Hey everyone, welcome back to our C# tutorial series. I hope you've been enjoying the journey so far and that you're feeling more confident with C#. In our last video, we took a deep dive into LNQ, learning how to query and manipulate data collections with elegance and ease. Today, we're tackling an absolutely essential topic in modern software development, asynchronous programming in C#. Whether you're building desktop applications, web services, or mobile apps, mastering asynchronous programming is key to building responsive, efficient, and scalable software. Have you ever had an application freeze while it's performing a task? Like when you're trying to load a large file or waiting for a network request to finish? It's frustrating, right? The app becomes completely unresponsive, and you're stuck waiting. That's where asynchronous programming comes to the rescue. It allows us to perform long-running operations like file reading, database queries, or API requests without freezing the main thread, keeping the app responsive and the user happy. So, what exactly is asynchronous programming? Simply put, it's a way to perform tasks in the background, without blocking the main thread. This keeps your application responsive, even while waiting for tasks like network calls or file I/O to complete. Think of it like ordering food at a restaurant. You place your order, and instead of standing by the kitchen waiting for your food, your waiter serves other tables, checks on drinks, and so on. When the food is ready, the waiter brings it to you without anyone having to sit and wait around. This is what asynchronous programming does. It allows your application to handle multiple tasks simultaneously, without waiting for one to finish before moving on. Let's break down why asynchronous programming is so important. There are three main reasons. Responsiveness. Applications need to stay responsive while performing time-consuming operations. Whether it's fetching data from a database, downloading files, or reading from disk, async code helps keep the UI smooth and responsive. Scalability. When dealing with multiple concurrent operations, async programming allows the system to handle more requests without creating new threads for each task. This reduces overhead and improves performance. Efficiency. By not blocking the main thread, we make better use of system resources. Idle threads aren't doing unnecessary work, allowing the system to perform optimally. In C#, asynchronous programming is mainly powered by the async and await keywords, as well as the task and task T types. So, let's start by exploring these in more detail. To get started with asynchronous programming in C#, we need to understand two key components, async and await. The async keyword tells the compiler that a method can run asynchronously. It allows the method to perform background tasks. The await keyword pauses the execution of the method until the asynchronous task completes. But crucially, it doesn't block the main thread during this wait. Let's see this in action with a simple example. Explanation. The perform task async method is marked with async and simulates a 2-second delay using task delay. Await tells the program to pause execution until the delay completes, but it doesn't block the main thread, allowing other tasks to run. You can see that even though the program waits for 2 seconds, it's still non-blocking and allows other code to execute smoothly. Now, let's talk about the task and task T types in C#. These are the foundation of asynchronous programming in .NET. A task represents a unit of work that runs asynchronously. Task T represents a unit of work that returns a result when it's done. The type parameter T is the type of the result. Let's see a more detailed example that shows how to use both task and task T. Explanation. The ComputeSumAsync method is an example of a task T, where it returns an integer result after simulating a delay. The printMessageAsync method is a task that doesn't return any result, but still runs asynchronously. Notice how easy it is to await the result of a task T, and how clean the code looks compared to manually managing threads. Now, let's address exception handling in asynchronous programming. It's similar to synchronous code, but there are some important things to keep in mind. When an exception is thrown inside an async method, it gets propagated when the task is awaited. You can use try-catch blocks to catch exceptions just like in regular code. Explanation. In this example, we simulate a division by 0 inside the divideAsync method, which throws an exception. The exception is caught by the try-catch block in the main method, and the error message is printed to the console. One thing to remember, exceptions in async methods need to be awaited, otherwise, they may go unnoticed. Let's look at how you can convert synchronous code to asynchronous to improve responsiveness and efficiency. Imagine you're reading a large file or making a network request synchronously. It could block the entire application. Here's a basic example where we read a file synchronously. Explanation. The file.readAllText method reads the file synchronously, meaning the app is blocked until the read operation finishes. If the file is large, this could take a while. Now, let's convert this code to use an asynchronous approach. Explanation. By replacing file.readAllText with file.readAllTextAsync and adding await, we can read the file asynchronously. This keeps the application responsive while the file is being read, instead of blocking the main thread. Converting synchronous I/O operations to asynchronous is one of the most common use cases for async programming. What if you have multiple asynchronous tasks that need to run at the same time? This is where task.whenAll comes into play. It allows you to run multiple tasks concurrently and wait for all of them to finish. Let's look at an example where we download multiple files concurrently. Explanation. We create an array of tasks that download files asynchronously using http client.getStringAsync. Task.whenAll is used to wait for all the tasks to finish before processing the results. This allows us to download all files concurrently, making the operation much faster than downloading them one by one. This technique is perfect when you need to run multiple independent tasks at once. As you dive deeper into asynchronous programming, there are a few best practices and common pitfalls to be aware of. Always await tasks. Make sure to await every asynchronous operation. Failing to do so can cause unexpected behavior or unhandled exceptions. Avoid blocking the main thread. Don't use .result or .wait on tasks, as they will block the main thread and defeat the purpose of async programming. Use task.whenAll for multiple tasks. When running multiple tasks in parallel, use task.whenAll to wait for all of them to complete efficiently. Use cancellation tokens. When working with long-running tasks, it's a good idea to use cancellation tokens to allow the user or system to cancel the operation gracefully. Test async code thoroughly. Async code can be tricky to debug, so make sure to thoroughly test different scenarios, especially race conditions or deadlocks. By following these practices, you can write clean, efficient, and reliable asynchronous code. Now it's time for the challenge. This will help you solidify everything you've learned about asynchronous programming in C#. Challenge: build a console application that downloads multiple images from the internet asynchronously and saves them to your local folder. You should provide progress updates for each download. Hints: use HTTP client to download the images. Utilize task.whenAll to download them concurrently. Implement proper error handling to deal with failed downloads. Bonus challenges: add a cancellation token to allow the user to cancel the downloads. Implement progress reporting to show how much of each file has been downloaded. This will help you practice both asynchronous tasks and file I/O, two critical skills in C# development. That's it for today's video. I hope you found this deep dive into asynchronous programming helpful and that you're ready to implement your own async code in your projects. In our next video, we'll dive into object-oriented programming and explore concepts like classes, inheritance, and polymorphism, so make sure to subscribe and hit the notification bell so you don't miss it. Thanks so much for watching, and I can't wait to see what you come up with in today's challenge. If you have any questions or comments, drop them below, and I'll do my best to answer them. Happy coding!